Good morning. Welcome to AP Stats. I know a lot of you are wondering, is today going to be yogurt day? And well, that was a while back. What we're looking at today is a warm-up problem. Warm-up problem here that has to do with interpreting the p-value where mu represents the mean AP stat score at Wheaton Academy from 2005-2018 AD. The null hypothesis is that the mean AP stat score is 4.05. Alternate that it's greater than that, and we have an observed mean AP stat score of 4.63 based on a sample of unspecified size. Let's see what the groups came up with. And I don't know if you're try to get a little bit closer to this. So I'm going to look first of all at the group 2 response. So the group 2 response is that the probability of 0.037 that we observe a mean student score of 4.63 or higher in the same size due to natural sampling variation, given that the true mean AP stat score 4.05 during 2005. Okay, so a good context here. Just looking at this one first. The probability, so coaching I would give here is that the probability is 0.037 that we observe a mean student score. So just to clarify this, it's not a huge issue, but what we observe is not the mean. The mean is behind the curtain. We are observing a sample mean. We observe a sample mean student score of 4.63 or higher. Thank you for putting the phrase or higher. That's a nice connection with the fact that in the diagram we're shaded to the right. So or higher is connected to shaded to the right. There's a word missing here or the phrase missing is samples of the same size due to either chance or natural sampling variation. Make sure you include the word alone. There's always going to be natural sampling variation, but we're talking about natural sampling variation alone, given that the true mean, true is fine, you don't have to have it there, parenthetical, of AP stat scores, is in there, is 4.05 during that time interval at Wheaton Academy. This was a Wheaton Academy context. So the Wheaton Academy context has to show up during the interpretation. So, I mean, I'd give it an E minus. I mean, it basically was there. Just some things can be, yeah, nice work, group 2. So, a little bit of feedback for, oh boy, battery. So it says battery's running low. Do we have a place to plug things in over here? Tell you what, I'm just going to pause the camera while I give the class feedback on statement 1, just so we don't run out of battery. And so plug in and pause. So nice work on the interpretation to the p-values. We're wrapping up this handout with the parking problem. Just to refamiliarize ourselves with the context, we're designing the downtown here for shoppers, and we built a new public parking garage in the central business district. Now, the city's planning to pay for the structure through parking fees. During a 2-month period, or 44 weekdays, the daily fees collected averaged $126 with a standard deviation of $15. And I believe that we did, okay. This part, yeah, I don't think we actually got to this part. So let's look at the assumptions. When you filled in the AB80 chart, remember that the assumptions for building a mu trap are the independence assumption and the normal population assumption. And we've never had to write those before. So here's your first example. of writing these out. Oh, I just remembered something. I remember where we were right at the end of class. I remember that that we were wrestling with this cattle thing, this cattle problem, and I was walking around the room, and a lot of you, some of you, seemed to think that letter C was an okay answer, an okay interpretation, which stated that we're 95% sure that the average weight gain among the cows in this study was between 45 and 67 pounds. This is the interpretation I've seen students mistakenly use most often. And there is a subtle difference. I mentioned it right at the end, but I just want to underscore this. That phrase in this study can turn an E into an I. This is an incorrect interpretation of a 95% confidence interval because we are 100% sure. We're 100% sure that the average weight among the cows in this study was, actually, we're 100% sure that it was, where is that actual 56 pounds? We're 100% sure that's 56 pounds. Do you need a copy? Yeah, of the handout. Does anyone else need a copy of the handout from the other day? Okay. Right there. Okay. So, yeah, what we're only 95% confident about is what's behind the veil, and that is the true mean weight gain. In our sample, it was 56 pounds, of which we are 100% sure. We're 95% sure that the average weight gain among all cows in this context was between 45 and 67 pounds. So that's how we ended class last time, is writing the correct interpretation of the confidence interval. So now I think we can actually go on to the next problem. Here, I've got written out for you some text regarding how to write the beginning of the paragraph, regarding the assumptions that you have to make. So here we go. I realize the text here might be a little bit small, so I'm going to read it for you at a pace that I hope you can keep up with in terms of writing stuff down. So here we go. The randomization condition. We're going to say that the weekdays were not randomly selected. So we're not satisfying the randomization condition. Let's be upfront about that. However, we will assume that the weekdays in our sample are representative of all weekdays. Right? And we have to make sure the sample is not too big, so we're going to check next the 10% condition. Both of these conditions team up to justify the independence assumption. Here's how we word the 10% condition. 44 weekdays are less than 10% of all weekdays. I mean, if you think about it, there have been a lot of weekdays so far, and way more than 440. I also want to let you know that on the AP test, they often don't even expect you to write down the 10% condition when it comes to hypotheses about means. Think of Dublin, Ireland, and the Guinness Beer Company. The example that's in our textbook. They weren't really worried about William Gossett taking too many samples. They were worried about him taking too few samples. So usually when it comes to sample means, the issue isn't that the sample is going to be too big. The issue has to do with small sample sizes. So I would, if I were you, I would just put the 10% condition in parentheses, because it's rare for AP stats graders to even be required by the rubric to read a statement about the 10% condition. What they will look for is your statement of the nearly normal condition. So here we go. Get ready to bring in the central limit theorem. For NNC, the nearly normal condition, you've never written this one before. Here's the statement. We don't have the actual data. But since the sample of 44 weekdays is fairly large, and we're thinking of 15 and 40 as the customary dividers between small, medium, and large. What's significant here is that 44 is greater than 40. So we are in large sample size territory. Since the sample of 44 weekdays is fairly large, it is okay to proceed. This is where the central limit theorem says, hey, it's okay. The shape of the sampling distribution of sample means becomes more and more normal for large sample size, or as the sample size increases. So 44, that means partnering with the central limit theorem that we are good to go. We are okay to proceed. And one other statement I'd like you to jot down here is that the weekdays in this sample had a mean revenue of $126 and a standard deviation in revenue of $15. So the sampling distribution of the mean, I'm going to fix my spelling error here, the sampling distribution of the mean can be modeled by a Gosset's T model. Oh, so sad. They didn't allow him to call it a Gosset's T model, so his pen name is a student's T model. If I'm not going to use the name William Gossett, what name can I use? Student. That's not a name. That's what you have to call yourself. Call yourself student. Final decision? Final. It's so lame. Joe. I heard that. Okay. So it's a student's T model with, you have to show your calculation on how many degrees of freedom. You can't just say a student's T model. There's an infinite number of student's T models. There's a student's T model with 1 degree of freedom, student's T model with 2 degrees of freedom. So you have to say with, not just with 43 degrees of freedom, you have to say where you got the 43. You have to say with 44 minus 1 equals 43 degrees of freedom. We will use a one sample T interval. That's the official name for the mu trap. And if you forget that, you can, it's actually on your calculator, which you can bring into the AP test. You're thinking AB, 80, 56, 24. Is he singing? No, this is not happening. But the traps are on the left. So if you forget the phrase one sample T interval, I mean, you know it's right there. It's a stat test 8. If you press stat test 8 on your calculator, the phrase one sample T interval will come up with 90% confidence for the mean daily income of the parking garage. Mean daily income of the parking garage. So that's the paragraph that I want you to learn how to write for the model section. Hypotheses, model, mechanics, conclusion. So the model includes writing about the conditions that justify the assumptions for the model, and then actually specify the model with a specified number of degrees of freedom. So, when I said back in August that this is a writing course, wasn't kidding. Okay. Do you have any questions on the verbiage that's required here? Required verbiage. Okay, I'll keep it there. But when it comes to writing a 90% confidence interval for the mean daily income, let's let's open up stat test 8. So I'm just going to pause here while we get our calculators out and run a stat test 8. Okay, so technically part of the model section is not only this verbiage, but also the bell curve that is a, not n for normal, it's a t sub, how many degrees of freedom? We calculated 43. So t sub 43 instead of n, with an assumed mean of 126 and an assumed standard deviation of 15. So instead of n, we're using t. This is a different model. Thanks to William Gossett, he was able to, without graphing calculators, he was able to do a lot of the work to find out what the actual equation was for this curve based on the number of degrees of freedom. We are assuming that the mean is 126. Had a mean revenue, okay. Ooh, sample mean. That's one of those ones. Daily fees collected. Okay. I just want to look at one more feature of this problem. And actually, there's something I'd like to bring your attention to in part E. In part E, it says the consultant who has advised the city on this project predicted that the parking revenues would average 130. And the reason I'm bringing your attention to that is because that's actually the null hypothesis. We're going to assume that the consultant is correct. So instead of a mean of 126, because that's actually just the observed mean, our null hypothesis is going to be that the consultant is correct, so that the mean is actually 130 with a standard deviation of 15. So here's the drama. The consultant said you're going to get $130 over that period, but our observation, when we open our eyes and look, it came out to only $126. So we'd like to know, well, one way to approach this is to ask for a p-value. Say, what's the probability that we observe a sample mean of $126 or less due to natural sampling variation alone in samples of the same size, samples of size 44, given that the consultant is correct? We could get a p-value, or we could construct a mu trap. If we do the p-value approach, we'd be interested in knowing whether the p-value is greater or less than what alpha level, class?
0.5.
0.05, which is 0.5 with an extra 0 in there. And or we could build a mu trap to see whether or not it contains or does not contain the predicted value. Friends, there's a nuance here in this problem. Here, we have someone coming in and saying, I predict it's going to be 130. It's going to be 130. Whereas in the video clip we saw last time, Prophet Jack comes in and says that the score in the game is going to be, Seattle, the Seahawks versus Broncos game is going to be 19-13. Why is it that Laney Kerrigan in the video clip assumed that what the person said up front was going to be false, where here we are assuming that what the consultant says is true? Why is it that when it came to Prophet Jack, we assumed he was not telling the truth, but when it comes to the consultant, that we assume he is telling the truth? What would dictate whether or not the null hypothesis is to believe what the guy says or not believe what the guy says?
Is this a rhetorical question?
No, this is a real question.
The confidence interval?
Okay, I'm hearing the confidence interval. Yeah, go ahead.
Prophet Jeff had no credible reason to know that information.
Yeah, he's a guy in the street.
Oh.
He doesn't have a credential. He's a homeless guy. So if it's a homeless guy, then the null hypothesis is that he's not, we should not believe what he has to say. But since this is a consultant, this guy's gone to the university. He's trained to make predictions like this. He doesn't live on the street, so there the null hypothesis is to assume that what he says is true. And that's the difference. It's a subtle difference, but that's the kind of thinking that the friendly people at College Board expect you to engage in when you take the AP test. So that's an important nuance. Thank you for engaging there. So, but here we're just gonna build a confidence interval and pay attention not to the alpha level, we're gonna pay attention to whether it contains or does not contain what the consultant said. So let's knock this out on the calculator. AB80, let's put the 8 in AB80, 5624. Stat, test, 8. So here we go. Are we inputting data or statistics? Well, we actually we observed, they're actually giving us the statistics. They've given 126 is a sample mean. That is a statistic. So you're gonna have to make that decision up front. And so, now this is making sense. The X bar that we observed was 126. And the sample standard deviation, notice it doesn't say sigma sub X, it says S sub X, and S means sample standard deviation. And that is, with our eyeballs, observed to be 15. They gave us a sample size of 44, and I think they're asking us to construct a 90% confidence interval, so we type in 0.90. So now it's going to build it for us. And just like it was last year, what a coincidence. It's still 122.2, 129.8. Do you think we're going to end up rejecting or failing to reject the null hypothesis? What? Sorry?
Rejecting.
Yeah, we are going to reject because does not contain means reject. Had it contained 130, we would fail to reject. So interpret the interval. So would you take a moment, I'm going to pause the camera, but take a moment to use a BOTS script to interpret this interval in the context of the problem. I'm just going to pause while you try that on your own at home. Okay, the camera's back on. And is there anyone who would be willing to give this a go, interpreting the confidence interval? All right, Andrew, you're on.
Based on this sample, we are 90% confident that the mean daily revenue at the parking garage, mean daily revenues at the parking garage are between $122.20 and $129.80.
Good job. Yeah, I'd give that a solid E, possibly an E plus. So that's had good context in it. And let's see what I have written up there. BOTS, BOTS. Based on the sample, we're 90% confident the mean daily revenues. Yep, there it is. So, and explaining what it means in this context, this is a review. A little bit unfamiliar because it means instead of proportions, but we can use the IRS script in repeated sampling. About 90% of samples of the same size collected using the same method will produce confidence intervals that contain the mean daily revenues at the parking garage. Then finally, the consultant who advised the city on this project predicted that parking revenues would average $130 per day. Based on your confidence interval, do you think the consultant was correct? And why? So we have to draw a conclusion. So, as you indicated to me earlier, you feel like rejecting the null hypothesis. You're right. We think the consultant is incorrect. The value of $130 is not contained in the confidence interval. Therefore, we have sufficient evidence that the mean daily revenue at the parking garage is less than $130. Maybe the clickbait sentence 3 would be, I hope this guy can find a new job, or this guy can't expect us to give him a favorable recommendation. Just pause here. Do you have any questions? This particular topic. Well, I'm going to leave that up there while I'm handing out the new handout. Yeah, go ahead.
So we are talking about the fiscal proportion, which means we have degrees of freedom. So do we have to mention that in our response?
The only place we have to mention degrees of freedom is when we're selecting the model, T sub 43. That's the only place we have to
That's
mention.
good for everything else. It's still going to be the same as the proportion, right?
Yeah, everything else will be the same, just trade out the concept of proportion, replace it with the concept of mean. Okay, so I'm gonna pause while we. All right, so we're on the next handout, labeled 9, or part 2 of 3 for inferences about means. And so up here, if you wrote that based on the sample of 95% confident that the mean household income of households in District 125 is between this number and that number, then you're good to go. And in repeated sampling, about 95% of samples of the same size constructed from about 95% of confidence intervals constructed from samples of the same size will contain the true mean income of all households in District 125. That's the right idea there. Let's take a look at these formulas, which we could have used to construct the previous confidence interval. We just went straight to the calculator and did it. But on that previous example we did with the parking garages, there is some work that we expect you to show. So let's just fill it in right here. The standard error of the sampling distribution of sample means is T star sub n minus 1 times the margin of error. And actually T star sub n minus 1. We have to get the formula for standard deviation in there, and that's actually my mistake because the T star actually goes on the margin of error. The T star sub n minus 1 times S over the square root of n. So the standard error, it's like the standard deviation, but we don't know the true standard deviation, so we take the sample standard deviation divided by the square root of n. So that's what should be written there. There is a star missing here, T star sub n minus 1. And so what we do is we take the observed sample mean, so x bar minus mu sub 0 over S over the square root of n, where degrees of freedom is n minus 1. Okay, so, yeah, this notation is an important issue here. We worked with the graphing calculator, and I know that, Chen, you said you had one of those graphing calculators that needed the program, kind of like Peter was using, but now you've got your other calculator. So, but to find T star sub n minus 1 for an 86% confidence interval, you'd have to use the inverse T command for some number, comma, and then you'd have to give it degrees of freedom. So since n is 37, degrees of freedom would be 37 minus 1, or 36. Last time we worked with this, I just told you the degrees of freedom. This time you say, oh, you didn't give me degrees of freedom. I'm going to have to calculate degrees of freedom on my own by remembering to subtract 1. Now, who can remember what number goes right here? What left area would I use for an 86% confidence interval?
-990.
Right, now, if we were doing TCDF, then, something like -999, comma, some t-score, maybe it's -1.5. That's the context in which we would use -999. But if I wanted to find an area, but here, I'm just trying to find a t-star. And so that means I need left area in this slot right here. What is the left area for an 86% confidence interval is my question. Now I'm hearing 93 coming from this corner of the room, which happens to be correct, 0.93. Because the other 14% has to be split evenly into the two tails. So 0.86, the other 14% goes 0.07 here, 0.07 there. So we've got a T star sub 36. The critical T value can be found. T star sub 36 can be found by taking inverse T of 0.93 comma 36. Just rehearse that procedure, those keystrokes on your calculator.
Would it be T star sub 37? Or would it
No,
say
it's always degrees of freedom here.
Okay.
So the first day we encountered these calculator skills, I gave you degrees of freedom, so you didn't have to subtract one. But when I don't give you degrees of freedom, you have to take the initiative to subtract one on your own. So what we're doing here is, so on the distribution menu, I'm doing inverse T of 0.93 comma degrees of freedom. If you don't feel like subtracting one, you can have the calculator do the work for you. And so we've got a T star of 1.509. Now, I just want to think through the notation with you to double check standard error. So, margin of error T star. Yeah, because it's always important to think about, are we going to include the star or not? And when it comes to margin of error, you probably remembered that when we were in the context of proportions, margin of error was Z star times the standard error of the sampling distribution of sample proportions. So this time, instead of Z star, it's T star. I could have written this formula as T star sub n minus 1 times the standard error of the sampling distribution of sample means. That's an alternate way to express that. I just happened to put in the specific formula instead of the more general expression here, but either one is acceptable as a formula for margin of error. Okay, so that's review. Andrew, go ahead, your
Can I
question.
please use the restroom?
Yeah, go ahead. Okay, let's go to page 2. And the stuff that you missed, you can just watch on video. Okay. Normal temperature. Now, this is an example that makes us question what it is we believe to be true. Like, if you just think about whether or not you have a fever, what have you been told your whole life that normal body temperature is for human beings? 98.6 degrees Fahrenheit. Now, that was around when I was a kid, and probably since the early 1900s. Not everyone has a normal body temperature of 98.6 degrees Fahrenheit. Some, due to just natural variation, some have higher, some have lower, and it's okay. But where did this 98.6 come from? Did they measure everyone's body temperature? It's an average. It's a mu. It's an average. And it was calculated. It's a statistic that came about using old technology. I mean, now they have some pretty advanced thermometers to take people's temperatures. I mean, you can Google the history of this. When did they first decide that normal human body temperature was 98.6 degrees? It's a long time ago. I mean, medical history is fascinating. I married into a family of doctors. I've heard some incredible stories of what happened in medical history, like, for example, blood pressure measurements. I mean, now you go to the doctor, they measure your blood pressure, no big deal. They just put that thing, they wrap that around, pump it up. It's a little uncomfortable. But do you know how they measured blood pressure as recently as the 1890s? I don't know if I should tell you this. It's a little bit upsetting. If talk about blood is upsetting to you, then you might want to just put some plugs in your ears. But they would actually have to slip open an artery and put a glass tube in there to see how far up your heart could push the blood. It was a very invasive procedure. So how do we see? Is Peter still breathing? How many students have just fainted? Okay. Now, friends, I tell you that story to get you to really question medical knowledge and how accurate it is. And that's what's happening in this study. What really is normal human body temperature? The researcher described in Exercise 9 also measured the body temperatures of what that randomly selected group of adults. Here's the summaries of the data. They want to see, we'll assume null hypothesis that it's 98.6 degrees. But let's take a sample. Okay, the adults are randomly selected, 52 adults or less. Okay, obviously we're not concerned that we're going to have too many adults in our sample given 7 billion people on the planet. Nearly normal condition, here we go. 52 is bigger than 40. So 52 is large, histogram shows no serious skewness, outliers, or multiple modes. Now friends, the good news is that when you're looking for the nearly normal condition, they won't always give you a number that's bigger than 40. Sometimes they'll just give you a histogram. And so you got to ask yourself, is it unimodal and symmetric? Because if the sample size is less than 15, then the central limit theorem does not kick in, because suppose it had been only 7 people. 7 is not bigger than 40. You can still proceed in terms of the nearly normal condition as long as the histogram is unimodal and symmetric with no outliers. So the nearly normal condition, sometimes the easy case is when you have a sample size bigger than 40. If the sample size is not bigger than 40, you're going to have to look at a histogram. And here's the bad news. If they don't give you a histogram, you have to construct one. You have to construct a histogram and look at it. And there's usually one problem every year on the AP test in the free response section where they give you some data and you have to build a histogram and say, look, it's unimodal and symmetric, so we can proceed, or that the nearly normal condition is satisfied. Sometimes they just give you the histogram and then you have to comment on that. So the people in the sample had a mean temperature of, ooh, look at this, 98.2846. That's the eyeball conclusion there. The eyeball statistic. Standard deviation of this, since the conditions are satisfied, the sampling distribution of the mean can be modeled by a student's T model with how many degrees of freedom? Class, how many degrees of freedom should we use here?
51.
Yeah, with 52 minus 1 equals 51 degrees of freedom. Now, and I just want to see where this is going. So that's okay. So it's a student's T model. We will use and I think what we're going to say there is a 98% confidence interval. I just want to double check on that. So, oh yeah. So here's the official name of it, and so it's a vocabulary issue. Which, if you forget the vocabulary, remember Stat Test 8 has it. It's a one sample T interval. So we can say we're gonna use a one sample T interval with 98% confidence for the mean body temperature. That's not a good sign right there, so.
I haven't happened in a while.
Feeling pretty good about that. So, select and lock. All right. Yeah, thanks for noticing. So, friends, we are working more today on that. Would you please use your calculator to actually find the 98% confidence interval for body temperature? And just gonna pause the camera as you use your calculators to build the mu trap. Okay, so since most of the work is filled in there for you, what we can do is just focus on that one piece with T star 98. So we're doing inverse T. And Chen, you still need the program, don't you? Or do you have a calculator that has inverse T or no? No, you don't. Okay, so let me get it for you during the next break here. But hopefully you did inverse T at 0.99, 51 degrees of freedom. If you did that right, it should have come out to be this number right here. That's the T star, so 51. Your calculator should give you 2.4017175. Okay, so I'm gonna give you an opportunity to do some homework on this. That will, turns out I'm out of the building on Friday of this week, so this will be due on Monday. But for building the mu trap, here's the work I expect you to show. Show the blueprints for building the mu trap in X bar plus or minus margin of error form, then put your margin of error formula in there and replace standard error of X bar with S over the square root of N. These numbers, which on the calculator, let's just verify this on the calculator. Using this data, fortunately, they give us the stats of 98.285. So into your calculator, please type in 98.285 degrees Fahrenheit. Seems a little bit cold. That's not 98.6 degrees Fahrenheit. The standard deviation in our sample was 0.6824. So even though they didn't give you that number in the text, don't be surprised if they give you a table of information that you can use to type this in. The count is 52, so they're giving us N is 52, and they're asking for a 98% confidence interval. So notice that the number here matches the number produced by your calculator, and when you're doing this for homework due Monday, let's see what else is actually provided by the calculator. This number was given in the table, 0.682379. Okay, I don't know where that came from because it looks like all we have is this. So that number is given, the 52 is given. The only thing that you have to do on your calculator before you get to stat test 8 is to do the inverse T. So that part is the inverse T of all this. And then to get from this step to that step, it's just a matter of copying down the interval, the mu trap that's produced. So do you have any questions as to what it is you'd have to, what work you would have to show when you're building a mu trap? Okay. So interpreting the interval. You know what, we've done a lot of work with this already today. We've explained, we've interpreted intervals. How about we skip down to what does it mean? Does our interval contain 98.6 degrees Fahrenheit? Does our interval contain the hypothesized value? No, it does not. So it does not contain mean reject. So we would say since the interval is completely below or does not contain the hypothesized value of 98.6 degrees Fahrenheit, there is strong evidence that the true mean body temperature is actually lower than 98.6 degrees Fahrenheit. Now that we have more accurate measuring instruments, it might be that we'll have to revise the medical textbooks or go on to Wikipedia and change the number a little bit. kind of makes you wonder what Wikipedia currently says about normal human body temperature. So let's find out wiki, normal human body temperature. Hopefully that's a safe search, not completely. So, oh, isn't that interesting? It actually varies by, what are we on, fever, 99.5.
37.5 person's body temperature is higher than 99.5.
37.5度就算了，好吧？
What? And, okay, so it's, notice they're acknowledging there's uncertainty here. They say that it's typically cited as 98.6 degrees Fahrenheit, but naturally varies from person to person by at least half a degree Celsius.
36度。
So, yeah, go ahead. Okay, so let's go on to our next page here.
37度其实还。
Okay, normal temperatures part 2. We're on problem 15. Consider again the stats about human body temperature. Would a 90% confidence interval be wider or narrower than 98% confidence? We've been down this road before. So friends, let's regroup. The 90% confidence interval would be narrower. The more confidence, the wider the interval has to be. We can be more confident with our interval when we are less precise. So let's think about that for a second. Does that make sense? That, yeah. See, a more precise interval would be a really narrow interval. So a really small margin of error would mean a lot of precision. So notice the inverse relationship between precision and confidence. We can be more confident with our interval when we are less precise. Less precise corresponds to a larger confidence interval. What are the advantages of the 98% confidence interval? Okay, well, 98% confidence interval has a greater chance of containing the truth, but the 98% confidence interval is less precise than the 90%. So advantages and disadvantages, I think you already have those filled in, so you don't need time to count that down. And furthermore, if we conduct further research, this time using a huge sample, 500 adults instead of only 52, how would you expect the 98% confidence interval to change? So think about that and try to fill in the words that would make that statement true. Have at it. Please raise your hand if you think you know whether the interval would be wider or narrower than the one we just built if the sample were increased from 52 to 500. Yeah, Andrew?
Wider.
Wider is the answer provided. Raise your hand if you agree with wider. Or interval. Now, no one agreed, but it could be that no one disagrees. I'll tell you, just to let you know, what we're looking for here is the blueprint for building that confidence interval is x bar plus or minus t star sub 499 times sample standard deviation divided by the square root of 500. We're comparing this margin of error essentially, which is a measure of wideness, to the other one, which was t star sub 51 times the sample standard deviation divided by the square root of 52. So the thing to compare here, the thing to think about is that a bigger number in the denominator is going to cause this overall fraction to be smaller. Because if you divide by a big number, you get a smaller fraction overall.
But would there be more margin for error?
Well, they're just asking about, they're asking you to compare the wideness of the interval. So, you know, we had a 98% confidence interval. Once you up the sample size to 500, that's going to decrease the margin of error because you've got a bigger number in the denominator, which is why it would be narrower. Narrower is what I believe is the correct answer. Do you have any questions on that? Yeah, so it'd be a lesser, smaller margin of error. So if you want smaller margin of error, you need to increase the sample size. Concept questions on that? We've done sample size calculations with p-traps. Now let's take a look at the sample size calculations with mu-traps. Remember, the hardest thing about sample size calculations for p-traps was that if they didn't give you a p-hat, then you had to assume a p-value. Nick, you probably remember this. What do we assume the value of p-hat's going to be if we have no other way to orient ourselves to it? Do you recall, Nick, what that is? What should we put in for p-hat when we're trying to calculate the sample size if we don't have a hypothesized value?
50. Oh yeah, 50.
50% or 1/2, you put in 1/2. So do we have to do something like that here? Well, here, how large might you allow? Okay, well, what if you want the margin of error to be 0.1? Is there anything comparable to having to pull a 0.5 out of thin air? Well, let's see, the margin of error is given at 0.1. T stars of n minus 1, we just use inverse t. Based on this, we use inverse t to get that number. And now this sample standard deviation, this is a little bit strange because yeah, if we were starting from scratch and we didn't already have a sample standard deviation, then we wouldn't have that number to put in. But since we'd already done a study and we want to ask ourselves the question, you know, how large would the sample have to be? We're going to take the standard deviation from the previous study. I just solved this for n. The algebra gives you 252. Okay, now, let's talk about some of the nuances here, because just like there was a nuance of assuming p-hat is 0.5, sometimes you run into a nuance here. Class? Here's what we need to focus on. Sometimes what we do is we use numbers from a normal model instead of a t model if we don't have enough information and we just have not even done any studies at all. So in this blank, I just want you to write inverse normal. If you have nothing to go on, I mean, think about it, this is kind of weird. Because inverse t assumes that you know the sample size. I mean, come on. Inverse t requires you to give left area and degrees of freedom. How on earth are we supposed to get degrees of freedom, which is n minus 1, if we're solving for n? Do you see the problem? Inverse t often does not work, but since we're talking about large sample size, remember that the limit as n approaches infinity of t sub degrees of freedom approaches a normal model. It approaches a z-score. So there's a nuance here also. If you don't know the degrees of freedom because you're trying to solve for n in the first place, then ditch inverse t and just use inverse normal instead. That's a nuance that's easy to forget. So you would use inverse normal of 0.99 because it's unreasonable to expect that you could use inverse t when you don't even know what n is in the first place. So watch out for that. Next page, late arrivals. So, will your flight get you to your destination on time? The U.S. Bureau of Transportation Stats report that the percentage of flights that were late each month, and they also give you a histogram, we can consider these data to be representative. There's no evidence of a time trend. So it looks like they have a correlation coefficient. So a scatter plot must have been involved at some point, but check the assumptions and conditions, which we've done here. Find a 99% confidence interval. So this time, there's some work for you to do. So would you please use your calculator to fill in the missing pieces of parts B and C? So I'm gonna let you work on that on your own. Take a look at the information in the chart. You may begin. Why do you think we, because this is Wednesday law, it goes to 12:40.
We're done.
But like they say, they extended the occupied.
Oh, they did extend it? Okay,
Well,
well,
outside world is
Alright.
I've just dismissed you 5 minutes earlier, so enjoy your extra 5 minutes.
The best meal.
Bye.